Hi, I'm Dane Quinn from the University of Akron, and today I'd like to discuss Lagrange's equations. This video lecture is for fundamentals of mechanical vibrations. So, momentum balance is probably the most common formulation that we use when deriving equations of motion. It's sum of the forces equals mass times acceleration, and then sum of the moments is equal to I alpha. Again, this is the one we learned first. It's the one that we primarily used in this class and probably any other class that you have taken in which you derive equations of motion. But it's not the only formulation that you've seen. When you took dynamics, we learned about work energy. So the work done from state 1 to state 2 is equal to the change in kinetic energy. The work is force dot path integrated from state 1 to state 2. And the kinetic energy is, for a particle, 1/2 mv squared, where v is the speed, or in vector notation, v dot v. So again, the change in kinetic energy is the work done. The other one that we learned is impulse momentum. So there, the impulse from time 1 to time 2 is equal to the change in linear momentum. And there's an equivalent version for angular momentum. But the impulse is the integral of the forces over time, and the linear momentum is the mass times the velocity of the mass center. Right? So again, these are two different formulations that we've used, and these are all equivalent. So if I use, say, momentum balance and derive equations of motion and make predictions, those predictions would be identical to the ones that I would obtain if I used work energy, right? So work energy and momentum balance are equivalent, and likewise, those are equivalent to impulse momentum, right? So all three of these things are, in a sense, different versions of the same thing. They can all be used to obtain equations of motion, and they all make exactly the same predictions if they're applied correctly. Now, these are not the only three. There are others, right? So in particular, in today's lecture, right, and for this section of the class, we will learn about Lagrange's equations. So Lagrange's equations are essentially another formulation for the equations of motion. They look a little bit different, but at the end of the day, we would have the exact same equations of motion that would describe the response of the system. So they're a different formulation for the equations of motion. These are particularly useful, we find, for multi-degree of freedom systems. Now, in today's lecture, I am not going to necessarily derive Lagrange's equations, but I do want to give you a sense of how they are obtained from momentum balance. Right? So I'll go through things fairly quickly. There'll be a lot of steps that I skip compared to a case where I was actually trying to go through the derivation. But again, I do want to give you a sense of what's going on in the development of Lagrange's equations. And then at the end, I'll do a quick example where I show the equations that we would get with momentum balance are exactly the same as the equations that we will get with Lagrange's equations. Right, so we start off with this and assume that we have a set of independent generalized coordinates. Right now, we call these generalized coordinates because they could be anything. They could be rotations, they could be translations, they could be some combination of the two. They're just coordinates that we use to specify the configuration of the system. And we assume that we start off with a set of independent coordinates. So if we have an n degree of freedom system, then we'll have n coordinates. We don't distinguish in Lagrange's equations from translations, which might be important for, for example, mass times acceleration, from rotations, which are related to angular momentum balance. All the coordinates in Lagrange's formulation are treated exactly the same. There aren't separate equations for this versus that, which is one of the nice things about this. Lagrange's equation starts off by defining a virtual displacement delta r. Right? So this is an unusual concept, right? Something you probably have not been exposed to before. But let me walk you through what a virtual displacement is. It's a displacement field, right? So when I say displacement field, it's essentially the displacement of all the different parts and pieces of the mechanical system that we're looking at. I have two examples here, a block and a pendulum. So here the displacement field will be how this block moves. And in this case, the displacement field will be how this pendulum moves. Right? So, but it's a displacement field obtained by an infinitesimal increment of the coordinates. Right? So whatever the coordinate is, I'll take that coordinate and change it just a little bit. Again, by what we think of as an infinitesimal amount. Right? So really, infinitely small. But the important thing is because we are incrementing the coordinates, the resulting displacement field has to be consistent with the constraints of the system. So here, let's look at an example. So this block might be naturally described by a coordinate that looks like x. Right? So here x measures the horizontal position of this block. And we might have directions I and j. So if I take this coordinate x and I increment it, then x goes to x plus delta x. So in this case, this block moves over by a small amount delta x. So here the displacement field, delta r, would be delta x in the I direction. Right? So again, the displacement field, we're asking, how does this block actually move? Well, again, x is incremented, so the block moves over. Now if I think about this pendulum, maybe I decide that I want a coordinate theta. Right? So theta is the rotation of this coordinate. Or sorry, theta is the rotation of this pendulum. Now I can define directions that are perpendicular to the bar and along the bar, say E1 and E2, like so. And of course, this bar has fixed length, right? So it serves as a constraint for the system. Right? In particular, let's do that in a different color. In particular, this pendulum moves on an arc. So if I increment this coordinate, I then ask, how does this mass move? Well, if theta is changed slightly, then the pendulum rotates just a little bit, and in particular, the mass moves in the E1 direction. Right? So here delta R is equal to, well, how much does it move? It moves by an amount L, where L is the length of the bar, delta theta in the E1 direction. So when I say infinitesimal and a virtual displacement, it's really highlighted here, because I couldn't take this pendulum and actually move it in the E1 direction by any finite amount, because as soon as it started to move, the direction would actually curve around the arc. But this virtual displacement is so small that you can think about this as almost being an actual displacement in the E1 direction. So Lagrange's equation starts off with this concept of a virtual displacement. Right? So let's see how that's used then. So I'm going to derive this, or at least I'm going to talk about this for a single particle. There are nice extensions to rigid bodies and that kind of thing. But to give you an idea of where this comes from, let's look at a single particle. So the only thing we have for momentum balance is sum of the forces equals mass times acceleration. Right? Linear momentum balance. So I'll take that equation and dot it with my virtual displacement delta r. So when I do that, I end up with the left-hand side becomes sum of the forces dot delta r. Right? So again, I take this and I move it inside, distribute it over there, and this quantity is defined as the virtual work. Right? So delta W. And then on the right-hand side, I have mass times acceleration dot delta r. And notice that because acceleration is the derivative of velocity, I can write this first term as the total derivative with respect to time of mass times velocity, or, in a sense, linear momentum. And then dot dr. So I'm going to look at this right-hand side first, and then on the next slide, I will look at the virtual work. So here, let's take this last piece. And I'm going to notice that if I take the derivative with respect to time of mv dot delta r, notice that's different than this because the derivative only acts on the momentum here. Then when I use the product rule, I get the derivative of the momentum dot delta r plus the momentum dot the derivative of delta r. Right, so again, this is just the product rule from calculus. This is how derivatives work out. But the thing that I notice is that this last piece, which I'm interested in for a single particle, actually appears right there. Right? So we can actually take this and solve for it. Right? So basically, that involves moving this. Well, actually moving this to the other side, right? So we see that the derivative of m times v dot delta r, which again, that's the right-hand side of the equations for momentum balance, dotted with the virtual displacement, is equal to, well, this piece that was on the left, so mvg dot delta r. And then I've moved this to the other side, so it gets a minus mvg dot the derivative of delta r. Okay, so now here is where I am going to skip over a lot of the math that is involved in deriving Lagrange's equations. I'm just going to kind of go to the almost final result. So it can be shown that this first term ends up reducing to the sum from j equals 1 to n of the derivative with respect to time. And now this is actually the partial of the kinetic energy with respect to q dot. So this term reduces to this. And then this term reduces to the partial of the kinetic energy with respect to q itself. And these coordinates are assumed to be independent, right? And so we have these virtual displacements here. And now I'll remind you, T is the kinetic energy, and it's m over 2 times v dot v. Kinetic energy. Again, there's a lot of steps that go from here to here. And I've skipped over those. I'm just trying to give you a sense of where Lagrange's equations come from. But essentially, this right-hand side ends up being written in terms of partial derivatives of the kinetic energy with respect to either the coordinates or the derivatives of the coordinates themselves. Right, so this is an important point, or an important step. And now let's go and look at the virtual work. So remember, for a single particle, we had the virtual work was essentially from the left-hand side, the sum of the forces pieces. And we just dealt with the right-hand side. So now for this virtual work, we can take these forces, all the forces that are applied to the system, they can be categorized into one of three types. They're either conservative, they are constraint forces, or they're something else, right? And which we'll call non-conservative. So let's look at those in turn. So we'll look at conservative forces first. So conservative forces are forces that are derived from a potential function or a potential energy. What does that mean? Well, that means that the force, these conservative forces, are related to the potential energy in the following way. F is minus the partial of V with respect to displacement, x, or in this case, our q's. So here, V is defined as the potential energy. So if we have a potential energy function, then we can use that, V, to find out what the forces are. Or, if we have the forces, if they're conservative, they are derived from a potential function. Springs are going to be the most common example for us. The second class are constraint forces. These are actually really important and one of the real values of Lagrange's equations. Right? So, constraint forces enforce kinematic constraints. Kind of right there in the name. So what are examples of constraint forces? Well, we saw two of them in the previous examples that we looked at. Let's go back. So here, in this block sliding along the surface, there's a normal force. I'm assuming this surface is frictionless, say, but there's a normal force that acts between the block and the surface. The purpose of that normal force is to not allow the block to move below the surface, right? So it constrains the block to lie on this horizontal plane. It is a constraint force. And notice that the direction of motion is always perpendicular to the plane. Therefore, when I look at the work done by the normal force, right, the normal force would be, say, in that direction, and the displacement would be in that direction. And so n dot x is equal to 0. Here, if I look at the pendulum, there's a constraint force from this rod. The fixed rod, or the rod of fixed length, enforces the circular motion of this pendulum, right? So there might be, in this case, a tension acting in this direction on the rod, and then the displacement of the rod would be in the E1 direction. So again, T dot x, x here represents the displacement, would be equal to 0. So this force does no work. So again, these constraint forces enforce kinematic constraints and do no work. Again, that's really important because what that implies is that F constraint dot delta R equals 0. Always. So the last class are non-conservative forces. And these are things that basically don't fit into conservative or constraint forces, right? They're just other. And so we just kind of have to leave them alone, right? We don't have anything that we can necessarily do with them. So now, if I go back and I look at the virtual work, virtual work is F dot delta R. So that's the conservative forces dot delta R plus the constraint forces dot delta R plus the non-conservative forces dot delta R. Now with this, these vanish because they do no work, and I'm just left with these two pieces. And now is where I'm gonna, just like I did with the kinetic energy, I'll skip a number of steps and I'll just kind of show you the final answer. And the final answer is that the work done, the virtual work from this displacement field, is the sum from j equals 1 to n. So again, over all of the coordinates, minus dv dq delta q. And these are the terms that result from the conservative forces. Kind of makes sense a little bit, right? These conservative forces are related to the potential energy, and then the potential energy comes down in the virtual work. We have 0 from the constraint forces, and then for everything else we just kind of lump that together, right? And it's going to be lumped together and called Q, and then delta QJ, right? So this is actually known as the generalized force, but you can see that force dot, or force times displacement, has units of work. And so the virtual work reduces down to these terms here. Again, I've skipped a lot of math going from here to there, but this is the final result. So when I put all this stuff back together, again, here I had my virtual work terms. Here I have my kinetic energy terms, right? So in particular, let's look at the stuff in the middle. We can combine these two terms, right? So basically I will take these pieces over on the left side and move everything to the right, right? So we have sums, we have delta q's, right? And so here we have the total derivative with respect to time. These again are partial derivatives. Kinetic energy with respect to q dot, partial with respect to q, and then again this comes to the other side, so it's plus partial of the potential with respect to q, and then the generalized force there. Now, since the coordinates are independent, we can change any one of them independently of any other. What that means is that I could take all of these delta qj's and set them equal to 0, right? Because this left-hand side has to be equal to 0. And then I could take just one of those. I could take all but one and set them equal to 0. And then I could take just one of them and make it something. Because this would have to vanish, that means that this coefficient has to vanish. And I could do that for every single equation, or every single coordinate. So since these are q's, then essentially this term in brackets must vanish for every single j. In addition, we find that v is independent of velocity, right, or the q dots, right? So what that means is the partial of v with respect to q dot is always equal to 0. And so now this term in brackets must vanish. And we can rewrite that as total derivative with respect to time partial of L, and I'll define L in just a second. Partial of L with respect to Q dot minus the partial of L with respect to Q equals the generalized force. And so this has to hold for every single coordinate. L here is the difference between the kinetic and the potential energies. So it's T minus V. So L is a function of Q and Q dot. And it's defined as the Lagrangian. And this is the fundamental quantity behind Lagrange's equations, right? So it's the kinetic minus the potential energy. Q is defined as the generalized force. Associated with the little qi coordinate. And it describes non-conservative forces. For example, damping. Now, if all of the forces are conservative, and all the forces can be either placed in the potential energy, or if they're constraint forces, then Qi, the generalized force, is equal to 0. So forces will either be placed into the potential energy, they will be constraint forces, in which case they do no work and we can ignore them, or they go into the Qi. I have not told you how to find this term. We'll save that for later, because initially we'll focus on conservative systems, where all of the forces will either be constraint forces, or they can be placed into the potential energy. Right, so let's look at our first simple example. Let's use Lagrange's equations and find the equations of motion for the spring mass system shown to the left. Now, we know the answer, right? So from momentum balance, right, or sum of the forces equals mass times acceleration, right, we can define, say, the stretch in the spring is x. We'll have I and j as our directions, and the equations of motion look like mx double dot plus kx equals 0. Right? So whatever we end up getting with Lagrange's equations should reduce to this, because this is the answer, right? We know that. We've done this 1,000 times. So now let's go through and try to model this system as if we didn't know about momentum balance and we wanted to use Lagrange's equations. Well, so we'll actually do the modeling in a very similar way that we started, or that we looked at with momentum balance. We'll first think about the response, right? So we'll identify the forces and the motion, right? So, well, and the objects as well, right? This is clearly a 1 degree of freedom system, right? So we only need one coordinate, and if this is the object, right, the force that acts on this system is due to the spring. Now, spring forces are conservative, right? They have a potential energy, right? So this force will go into the potential energy, and there are no other forces. So this is a conservative system. The second thing we will do is coordinates and directions, which I've already defined here. Right, so now, when it comes time to talk about the kinematics, right, we have to find the velocity, because the velocity is what will be used for the kinetic energy. And the velocity of the mass, in this case, is x dot in the I direction. Right, it's just this coordinate in the I direction. Right, so the kinetic energy in this system is 1/2 m times v dot v. So that's x dot in the I direction dot x dot in the I direction. Right, so we end up with 1/2 m x dot squared. And the potential energy in a spring is 1/2 k times the stretch squared. And of course the stretch here is x, so that's 1/2 x squared. Right, so now we can form the Lagrangian. And its L is T minus V, so it's 1/2 m x dot squared minus 1/2 k x squared. And of course, in this case, the system is conservative, so the generalized force is equal to 0. Finally, we need to go and apply Lagrange's equations. So here they are again. I just rewrote them. The system has 1 degree of freedom, right? So n is equal to 1. And essentially, this first generalized coordinate is x, right? It's the only coordinate we used. So now, I'll remind you, L in this case is m over 2 times x dot squared minus k over 2 x squared. So we need to calculate, well, first we'll calculate these partial derivatives. Right, so let's calculate the partial of L with respect to x. Well, so partial of with respect to x of m over 2 x dot squared minus k over 2 x squared. So remember, with partial derivatives, essentially we think about x and x dot as independent quantities, right? So take the derivative of this with respect to x while holding x dot fixed. We're thinking of x and x dot again as independent pieces here, right? So this is independent of x because again x and x dot are distinct things here. So the partial derivative of this with respect to x is equal to 0, and then we just take the derivative of this with respect to x and we get minus kx. So now let's take the partial of L with respect to x dot, and we'll do the same thing. M over 2 x dot squared minus k over 2 x squared. And we see that this term now becomes mx dot, and then the derivative of this with respect to x dot is equal to 0. So as a result, Lagrange's equations become d dt of partial of L with respect to x dot minus the partial of L with respect to x equals 0, right? So we have the total derivative of mx dot, right, because that was the partial of L with respect to x dot, minus, now this term is minus kx equals 0. And what we're left with, well, taking the derivative of this with respect to time, it's just mx double dot minus minus plus kx equals 0. So this is great, right? Because this is identical to the equations that we would have obtained, or that we did obtain, with momentum balance. Granted, this is a pretty simple example, right? But it is comforting to note that applying Lagrange's equations gives us something that's identical to what we would have gotten in our more familiar momentum balance equations. Yet, you have to admit, this looks completely different. Right? So here we calculate energies, kinetic and potential energies. We have velocities. The acceleration never appears explicitly in this formulation. We have a Lagrangian. We take partial derivatives and total derivatives, and then somehow we get the same thing. And this is how it works. These two formulations are entirely equivalent to one another. So we can use momentum balance, we can use Lagrange's equations, we could even go back and use work energy or impulse momentum. But here we're going to focus on Lagrange's equations because they really are convenient for multi-degree of freedom systems, especially conservative multi-degree of freedom systems. Okay, so that's it. That's a lot to take in. And again, the purpose of this lecture was not to necessarily derive Lagrange's equations strictly, right? But it was to give you a sense of how they are obtained, right? So if a lot of those intermediate steps seem fuzzy, well, they're probably supposed to, right? Because I skipped a lot of math in getting the potential energy into these equations and the kinetic energy, all right? So I'm just trying to give you a sense. But I hope that was helpful, and thanks so much. I will talk to you soon. Take care. Bye.